Welcome back to Recreational Sniper. Tonight it's Friday and I'm starting a new thing here. Every Friday we're going to work on a new firing solution. So we're going to call this Firing Solution Friday. So today we've got to calculate a firing solution for this problem. Now I've already done this in advance for this first one. In the next video, next weekend, next Friday, I will go with you guys through this whole process. So, for this first shot, we're going to shoot a range of 1,137 yards at an elevation of 1,233 feet. And we're shooting at a shot angle of negative 15 degrees, so we're shooting downhill slope 15 degrees. Temperature is 80 degrees Fahrenheit, humidity 50%. The latitude is 34 degrees, 44 minutes, and 15:28 seconds. The azimuth we're shooting on is 294 degrees west-northwest. So that's a lot to take in there. So let's kind of break this down a little bit. I didn't make this one too complicated. And the rifle we're using is my .308, and we're using the drop charts that I have made for my .308. This first drop chart is geared for 2992 inches of mercury, 0 feet in altitude, so we really don't need that one. From there, I go up in 1 inch increments. So my next chart is going to be 29 inches of mercury, which roughly 899 feet. On average, not exact, but on average, that's what you would have at that barometric pressure. And then the next chart above that is at 28 inches of mercury there, and we're at 1,910 feet. So we're in between 29 and 28 inches of mercury. Okay, so we're not exactly at either point because we know that we are at 28.67 inches of mercury for the shot. So how do we use our drop charts now that we set these up in increments of 1 inch of mercury? Because if we were to have a drop chart for every 1/100th of an inch of mercury, or even 1/10 of an inch of mercury, we would have tons of drop charts for each altitude, for each inch of mercury. And then we would have these drop charts also divided out into temperatures for that, and it would just be tons and tons of data and tons of paperwork and charts to keep up with. And then out in the field, you would have to dig through tons of that crap just to be able to, find the right firing solution, So we're going to do a thing called interpolation, which is kind of a scientific method of it's more than an educated guess. It's not just like an educated guess, but it's more than that. It's actually like more or less a calculated educated guess. And by that, we are going to be doing some calculations here. So, first things first, we got to figure out our actual range. So 1,137 yards is what we're getting, right? But say we're using a rangefinder, and this is the scenario we're going with. Say we're using a rangefinder that just measures the true range, the straight line range from your eye through the rangefinder to the target, and it gets 1,137 yards, but you're shooting at a 15 degree downward angle. Okay, so your horizontal range is going to be a little bit different than that. So say this is your firing position here, and your target is here, and your horizontal range is going to be on this plane, and your true range that you're measuring is on this plane. So this is 1137, but you're shooting at a 15-degree downward angle, right? So this is where your scientific calculator comes into play, and you're going to need one of these. You're going to need to be able to do trig functions to make this work. So you need a scientific calculator. They're pretty cheap. The one that I normally use is just a Casio. You can use like a TI-30. You know, you can buy these calculators at Walmart for between like $10 and $20 depending on the model. And if you want to go up from there, if you want like an actual graphing calculator, like a TI-83 or 84 or something like that, you know, you could pay $100 to $140 for them, but you don't really need that. The one I use is like $20. It's a Casio. Anyways, so you're going to need to be able to use a cosine for that degree of slope. So we know that our slope is 15 degrees, so we're going to take the cosine of 15 and we're going to get 0.9659. So basically that is your percentage of what, you know, we're going to multiply this percentage times the range that our rangefinder is giving us, which is our true range again, and not our actual horizontal range. Now I know with modern newer rangefinders, like even the one that I use, which is a Vortex Razor HD 4,000 yard rangefinder, it has a setting in it that will actually give me my actual horizontal range if I just set it to that versus the true range, and that alone will cut out this quite a bit of the equation here. But we're just going to pretend that my rangefinder is set for true range and not actual horizontal range. So we're going to calculate our actual horizontal range here. And so we'll take our 0.9659 and we're going to multiply that by our 1137 yard range, and we're going to get 1098.2 yards of actual horizontal range, or AHR. Okay, now we're not done yet, not by a long shot. So now we got to interpolate between, we got to figure out where we sit at 28.67 inches of mercury. So we've got our charts, and they're either at, you know, we've got one at 29 and we've got one at 28. So we're going to take a look at the 29 first, because that's the lowest in altitude. The more dense your area is, the lower you are in altitude typically. So we're going to look at, you know, and we're looking at, we're not quite 1,100 yards. We're 1,098 yards. So we're in between 1,000 yards and 1,100 yards, and that's important. So we're going to go ahead and take a look at our 29 degree chart here, our 29 inch of mercury chart. And we're going to go down here and we're going to look at 1,000 yards. Okay, so at 29 inches of mercury, we have a 11.8 mil of drop according to this chart. If everything's perfect, of course, these were all recorded at 80 degrees Fahrenheit and 50% humidity. I'm going to go ahead and note that I did not do any humidity or temperature change for this shot. We just changed altitude basically. So we're not going to really get into the whole temperature change thing. We're just going to look at, you know, that's going to be an even more advanced calculation if we're shooting in a different temperature range or shooting in a different humidity range. All right, so say it's 80 degrees and 50% humidity, and the only thing that really changes where we're shooting at, and we're shooting at a higher altitude. So we're looking at our 1,000 yard drop is 11.8 mils, and our 1,100 yard drop is 14 mils. Okay, so we're going to go ahead and we're going to make note of that, and we're going to subtract 11.8 from 14, and we get a difference of 2.2 mils. Okay, and then we're going to multiply 2.2 by 0.982, or which would be 98.2% of the difference between 1,000 and 1,100 yards. So we're not quite 1,100 yards. So we are 98.2 yards between 1,000 and 1,100, if that makes sense. So 98.2%. So that's easy to just say we're going to multiply 2.2 by 0.982, and we're going to get 2.1604 as our difference there, or sorry, as the amount. I'm tired. As the amount we are going to increase by. So we're going to take the small number, the low number at our 1,000 yard mark, which was negative 11.8 mils, and we're going to add 2.1604 to it, and we're going to get, we're going to convert that. It's going to be negative 13.9604 mils. Okay? So that's part one. Part two is now we've got to do the same thing for 28 inches of mercury. And for 1,000 yards, we're going to look at that. It's 11.6 mils of drop. 1,100 yards, it goes to 13.7 mils of drop. So we take 13.7 mils, subtract 11.6, we get 2.1 mils. And again, we multiply that by 0.982, and we get 2.0622, and we're going to add that back to 11.6, and we're going to get 13.662. Okay, so then we're going to take the big number, 13.9604, and we're going to subtract 13.662, and we're going to get a difference of 0.2982, and then we're going to take that, because it's the difference, and we're going to multiply that by where we are in between 28 and 29, which is 0.67. And we're going to get 0.199794. And we're going to add that back to the low number here again at 13.6622. And we're going to get our final adjustment just for our elevation at the specific range of 1,098.2 yards. We're going to get 13.861994 mils. And the reason why we are doing our actual horizontal range, which is 1,098.2 yards, and not the true range, which is 1,137 yards, is because our actual horizontal range is the distance that gravity is actually affecting the bullet, that gravity is actually pulling down on the bullet. Okay, because we're shooting downhill, the bullet is actually only traveling forward 1,098.2 yards, even though because of the angle we are shooting through the atmosphere, it's traveling 1,137 yards, but gravity is only affecting it for 1,098.2 yards. So that's the reason why we're doing this. And so our actual adjustment is roughly 13.9 mils. And if you're wondering if that's even correct, you can actually go ahead and plug this this information up here. You can plug this information in to a ballistic calculator, and the one I like to use is JBM Ballistics, but you can use others. You can use Hornady, you can use Berger, you can use any of those guys that have a ballistic calculator that allows you to put this information into. And as long as you put everything in correctly, that you are, the direction you're shooting, the angle you're shooting, the altitude, and the barometric pressure, the temperature and humidity. As long as all that stuff is correct, and don't forget the angle, you're shooting downhill. When I plugged all of that into JBM Ballistics, it come out to 13.9 mils, which is almost exactly what I got, because, you know, when you're indexing your scope, it's in 1/10 MRAD or 1/10 mil adjustments. So the smallest adjustment I can make is 0.1. So we would have to round this number up to 13.9, and that would be the closest correction I could make, and which is what JBM Ballistics calculates it out to be, is 13.9 mils. So we did good there. All of this math here is correct, and we're good to go at that point. So we've got our vertical corrected so far. Now we're going to move on to our spin drift. Okay, so spin drift is important. It's more important than Coriolis by a lot, but your Coriolis does come into effect about 1,000 yards, and we're going to get into that. But first we're going to mess with spin drift. And we're kind of going to have to do about the same type of thing. Is we're going to have to do calculations for both of these charts, and we're going to have to average them out, and then use the difference, and use that, you know, our 67%, which is, you know, what we use there. To get our spin drift corrected, we're going to have to correct our gyroscopic stability factor. We're going to have to correct that first. So, correcting the gyroscopic stability factor, we know, because I already went through the trouble of doing this, sorry if that's not going to focus, but up here in the corner at our 29 inches of mercury chart, we've got a gyroscopic stability factor of 2.13, and then at a little higher altitude here, it goes to 2.22. So we got to figure out where we are in between those two numbers. Alright, so we're going to take 2.22, and we are going to subtract 2.13, and we're going to get a difference of 0.09. And we're going to multiply that by 0.67 again, because that's our difference. We are 0.67 in between we're 0.67 in between 28 and 29. So, and we're going to get 0.0603. Okay, so we're going to add 0.0603 to 2.13. which is the low number. Again, we always add to the low number. And then we're going to get a gyroscopic stability factor of 2.1903. We're going to round that up to 2.19. And then, so now we've got to mess with time of flight, because the equation for figuring out your spin drift requires your time of flight. So at 29 inches of mercury at 1,000 yards, their time of flight is 1.737, and at 1,100 yards, it's 1.994 seconds. So we're going to take 1.994 seconds minus 1.737 seconds, and we're going to get a difference of 0.257 seconds. And then we're going to take 0.257 seconds, and we're going to multiply that by 0.982, which is our difference in yardage in between 1,000 and 1,100 yards. And we're going to get 0.252374 seconds. And we're going to add that back to the low number, which is 1.737. We're going to get 1.989374 seconds. Okay, and then we're going to go and do the same thing for 28 inches of mercury at 1,000 yards. Our time of flight is 1.713, and 1,100 yards, our time of flight is 1.962. And so we're going to take 1.962 minus 1.713, and we're going to get 0.257 0.249, and then we're going to do the same thing. We're going to multiply 0.249 times 0.982, and we're going to get 0.244518. We're going to add that back to the low number again, 1.713, and we're going to get 1.95758. Okay, so now we've got our 29-inch flight time and our 28-inch flight time differences, and now we've got to average those together. And if you want to do that, you can take the big number, subtract the small number, then you get a really, really tiny number, and then you have to multiply it by the altitude again, back up there at the 0.67. So you get, well, I'll just do it anyways. I'll just go over it. So you take 1.989374 and you subtract 1.957518, and you get 0.031856, and so you take that and you multiply it by 0.67, because we are 67. If you can see that we are at the 67 in between 28 and 29. So we're going to get 0.02134,352 down here at the bottom. And now we're going to flip the sheet over. We're almost done here. This is spindrift thing's kind of complicated, but anyways, we're going to take that number and we're going to add it back to the small number, which is 1.957518, and we're going to get 1.97886152 seconds. We're going to go ahead and round that up to 1.979 seconds. All right, now here's our formula for the spindrift. Now that we've actually figured out our time of flight, we've interpolated our time of flight, and you know, it's not exactly 100% correct, but it's pretty damn close. So our spindrift formula is 1.25 times the gyroscopic stability plus 1.2 times the time of flight to the 1.83 power, and that will give you your drift in inches. So we're going to do this here. 1.25 times 2.19, which is our gyroscopic stability, and plus 1.2 times our time of flight, which is 1.979, and we're going to raise that to the power of 1.83, and we're going to get a spindrift of 14.778 inches. All right, so now we've got to convert that to mils so we can actually adjust that on our scope. And being that this is a right-hand twist barrel, our spindrift is going to the right. So 1 mil at 1,098.2 yards, we can calculate that by 3.6 times 10.982, and we're going to get 39.53 inches for 1 mil at that range. So we're going to take our spindrift of 14.778 inches, and we're going to divide it by that 1 mil value of 39.53 inches, and we're going to get roughly 0.374 mils of spindrift. So we are in between 3 and 4 clicks on the scope, and we're right in the middle in between. So we could either go 3 or 4 clicks, and it would work good either way. I actually would probably lean towards 4 clicks because we're a little bit closer to 4 clicks than we are 3 clicks. So 4 clicks on the scope, and we're correcting back towards the left because we have a right-hand twist barrel, so our spindrift is to the right. So we're going to correct back left 4 clicks, and that's our spindrift. Now we're going to get into horizontal Coriolis, and actually surprisingly the horizontal Coriolis and vertical Coriolis are a little bit easier to calculate, a little less complicated actually. So for the Coriolis effect, we have to know our range in feet now to be able to get our deflection in feet. We also have to know this value called the omega constant, which has to do with the rotational spin of the Earth. And the omega constant, for you guys that don't know, is 0.00004, or sorry, it's 4 zeros, 0.0000729. So that is your omega constant. Go ahead and take a minute to memorize that, write that down. It's very important. You have to know that that is what the omega constant is for your horizontal and vertical Coriolis. So from there, let's go ahead and convert our yards to feet. So we're going to take our 1,098.2 yards. We're going to go ahead and multiply that by 3, and we're going to get 3,294.6 feet. All right, now we're going to plug that into this equation. We're going to take our omega constant, 0.0000729, and we're going to multiply that by our range in feet, which is 3,294.6. And by the way, the reason why we're using our range, our actual horizontal range, is because that, when you're talking about Coriolis effect and stuff, you're going to need the actual range that you are, the distance you're going across the face of the Earth. It doesn't matter whether you're up on a mountain shooting down, or down in a valley shooting up, and you're shooting way further than, your actual horizontal range. This requires your actual horizontal range. So pretty much you're going to end up using your actual horizontal range more than anything else for these calculations. So anyways, we're going to multiply our omega constant by our actual horizontal range in feet, and then we're going to multiply that by our time of flight again that we did all of that calculation for earlier for spindrift. Now we're going to need that number again, so 1.979 seconds. And then we're going to multiply that by the sine of the latitude that we're on. Okay, so there's a couple different ways of doing this. It's kind of difficult. I actually don't know the calculation to convert your degrees and minutes and seconds to an actual decibel value, and I need to learn that so that I can help teach you guys a little bit better. This part I actually did have to look up how to convert that, and I ended up using an online calculator, which kind of goes against the whole point of knowing how to do any of this shit by hand. Is well, the whole point of that is in case you don't have internet access. So it's one of those things, a little bit of a flaw in the system. I do need to figure out how to get this value from our latitude there that we got from our GPS. So anyways, if you convert our 34 degree, 44 minute, 1528 second latitude, and you can convert it to a decibel, you will get 34.73337578 as a latitude there, is in a decibel form. And you will get that, and once you do this calculation out, you actually get this value, and it's in feet. So 0.2708359,132 feet. And then we're going to multiply that by 12 inches so we can get our inch value. How many inches is that going to be? It's going to be 3.250030958 inches, and we're going to round that up to 3¼ inches. And we're going to divide that by our 1 mil value in inches at our range, which is 39.535 again. And we're going to get a correction of 0.08221 mils. So just under 1 click on the scope for horizontal correction. Now, anytime you change latitude and that sort of thing, you're gonna end up changing correction on that a little bit. Depending on the latitude you're on, it's going to change a little bit, but one thing that's important to know is horizontal correction. You're going to have horizontal Coriolis irregardless of whichever direction you are actually firing, whether it's north, south, east, west, doesn't matter. You're going to have a horizontal Coriolis correction, and in the northern hemisphere where we are at, it's always to the right, so which means we have to correct back left 1 click. So we can add that 1 click to our, and it's almost 1 click, and we can add that to our spindrift, and so we are actually, if we go 4 clicks, we're actually going to be closer to, if we just go ahead and go 4 clicks, we're going to be pretty good to go. We probably won't have to go 5 clicks back left, but 4 clicks will go great if we do our horizontal with our spindrift. All right, so horizontal Coriolis and vertical Coriolis are both very, very small measurements, and they really don't come into play until you're beyond 1,000 yards. Like here, we're looking at almost 1,100 yards, and horizontal Coriolis correction is not even 1 click. It's almost 1 click. It's 82% of 1 click, so we could go ahead and bump it up to 1 click, but yeah, your margin of error as a person shooting that far is probably going to be greater than that 1 click on your scope. Anyways, if you're super, super confident and you're shooting something super, super small and you're confident in your ability to be able to hit something that small, then it is going to be important to be able to calculate that out and then actually correct for it. So on from there, we are finally getting to our vertical Coriolis effect, and this is actually going to be important whether you are shooting east or west, that direction, and how close you are to shooting east or close you are to shooting west is going to be important, because your maximum values are going to be due east or due west, depending on whether you're going to have to bring it up or bring it down. And then your north and south, if you're shooting due north or due south, your values for vertical Coriolis would be 0. And you can kind of play with this if you want to, but I'm going to go ahead and run through the scenario that I've got here and finish this up for you guys. I know it's overwhelming how much math this is, but more or less this is exactly what a ballistic computer is figuring out for you. The difference is we're doing this by hand, using using the tools we have, a scientific calculator and a weather meter. If your ballistic calculator isn't working, you can still manage to do this stuff by hand. So, provided of course you have a graphing calculator with trig functions. All right, so vertical Coriolis, let's get into this. So we're going to need that omega constant again, and we're going to need our range in feet again and our time of flight again, but we're going to have a little bit of some different stuff down here going on. So we're going to go ahead and take our omega constant, we're going to multiply it by our range in feet and by our time of flight to the target, and then we're going to multiply that by the cosine of our latitude. And this time, just for heaven's sake, I went ahead and rounded that number up to 34.7334. And then we're going to go ahead and multiply that by the sine of our azimuth. So the azimuth is the direction you are actually firing. And our azimuth is 294 degrees. And if you're looking at a circle here, you've got 360 degrees, and so if your due north would be 0 and due south would be 180, east would be 90, west would be 270. So if we're shooting 294 degrees, we're somewhere in here. So we're shooting west, northwest. All right, 294 degrees. And then we get the value from that, and we kind of round it down or round it up. We get 0.3568, and we're going to take that, and that's our correction in feet. So we're going to take that again and multiply it by 12, and we're going to get a horizontal, a vertical Coriolis change of 4.28213 inches, and then we're going to divide that by our inch value for 1 mil at our range, again, of 1,098.2 yards, and which is 39.535 inches, and then we're going to get 0.10831 mils, so literally 1 click. And this is where it's important, but because we are shooting west, and our sun rises in the east, which means we are rotating towards the east. The earth is rotating east. Our target, if we are shooting towards the west, is actually rising towards us. So our bullet impact is going to hit down. It's going to hit low. So we are actually going to have to add a mil up. We're going to have to add that to... We're going to have to add that, or not 1 mil, but 1/10 of a mil, 1 click. We're going to have to add 1 click back to here. So instead of 13.9, we're actually going to need to dial up to 14 mils even to be able to hit this target. So provided that there's absolutely no wind, because I did not add a wind correction to this, even though I had plenty of room on the paper to do so. We'll do that next week. We'll do a different one, and I'll have my calculator, hopefully, if I can find it, and I'll actually work through this whole process with you guys. And we'll do one with wind at a totally different altitude and stuff, and we'll do this stuff together. So anyways, you're gonna have to add that 1/10 of a mil, 1 click, to your original vertical adjustment, which was 13.86, or you could round it up to 13.9, and then add that 1 click to it. So you would end up getting 100, or 13, sorry, you would end up being 14.0 mils. So 14 mils even, which would be 140 clicks up on your scope to get to your target at 1,098.2 yards. And there you go. And then your horizontal, of course, is going to be right at, we're going to go ahead and say we're going to go right at 4 clicks back left. Again, this would work great if it was dead wind, no wind at all. And our humidity and temperature were the exact same as on our ballistic charts. That's how this would work. Now, if our humidity and temperature were different than what was on the ballistic chart, well, I've got a lot more data gathering to go. You know, I've got to gather data in the 90 degree, 100 degree, 70 degree, 60 degree, you know, all the way down. And, you know, I would at least be able to get me a good temperature range change. But if, as far as humidity goes, if the humidity changes a bunch, you know, beyond 1,000 yards, I really think that humidity out to 1,500 yards to 1,700 yards is probably really not a factor, which is the reason why I go ahead and I do my charts and I just set them at 50% humidity, because if I'm somewhere between 50 and 100%, or if I'm somewhere between 0 and 50%, depending on the day, the amount of change that's actually going to occur and the amount that's actually going to affect the flight path of the bullet is so minuscule that unless I'm shooting 2,000 yards, it's not going to make much of a difference. Like, it's not going to make enough difference to actually be able to correct for it in the scope, because the clicks in the scope are bigger than what the correction value would be. I mean, we're talking at 1,000 yards. If there was a full swing of the humidity range, like from 0% all the way up to 100%, say my charts and everything were calibrated for 0% humidity, and then I had to go and I had to make this shot at 100% humidity, the correction at 1,000 yards would not even be 1 mil. It would be about half of a mil, give or take, which is not even enough to, you could not index that in your scope turret, you know, because we're in 1/10 mil scope turret adjustments, and we would be, you know, our humidity change would be like half of 1/10 of a mil, is what I'm trying to say. It's very, very, very small. So maybe at 2,000 yards you might want to start trying to be able to account for humidity, but 1,000 yards, even 1,500 yards, I really wouldn't worry about it. This is going to get you close enough. If you can do this, you're going to get close enough. So anyways, that's going to be it for tonight. I know this is a long video. There's just an absolute ton of information we just went over. And you kind of got the gist about why and how I set my charts up. And I keep my time of flight over here now for my standard conditions, quote unquote standard conditions, because you know, what are standard conditions? There's really no such thing, but you can find conditions that are relatively, you know, standard in your area. And that's basically what I've done, is the conditional average that is typical in my area is basically what I have in my chart, you know. So I'm going to get pretty dang close using that to being, you know, when I have to calculate for a different area. So anyways, it's getting late. Been going on and on for about 40 minutes now, and yeah, we'll see you guys next time in the next video. Thanks for watching. Leave your comments and questions below, and I hope this gave you guys some good information, and maybe maybe some of you guys out there find this stuff kind of interesting. I do. It really just gets me, you know, being able to do this kind of stuff. And it's kind of funny because I used to really hate math, but now that I've gotten into shooting long range, I've got a totally new outlook towards math, and it's really, really fun to be able to calculate precisely what you need to do for any range. You could just throw a random range and altitude out there, and with the right formulas and right inputs and everything, you can make it work, and that is super cool. So I hope you guys feel the same way about it. If you got some questions or comments, leave those below, like I said, and we'll see you next time in the next video. Thank you guys for watching.